So yesterday we did question 1 from this 2014 paper. Any questions or queries from yesterday at all? Any particular questions or requests or queries for this session? Anybody's got? No. Okay, then in the absence of those, I'll just keep going through discussions based off these questions. We may address the various issues as we get inspired to from these questions. If you've got any related questions as we go through, please feel free to ask me those. And in advance of the lecture next week, if there's any particular questions or queries you'd like me to address, or any tutorial questions you'd like me to go over again, please feel free to suggest those. Ideally, email me in advance so I can be sure, to prepare something or to make sure we can fit it in next week. Okay? And I'll be seeing you for the tutorials next week as well, on Friday of next week. Okay then, so looking on at question 2. Question 2, we're going to some slightly later material here, so we're looking at congruences and the order Trojan here. Question 2a is the kind of easiest bit here. And again, these are marks that everybody should be picking up. Everybody should be picking up these without any fail at all, because this is such a basic concept. To define one, state the definition of the congruence relation. So you're given the congruence relation in notation there, and how does it relate to the remainders left when the integers a and b are divided by n? So for this, again, this is a basic definition. You should have things like this very well prepared, practiced, and if you're so familiar with them, they should naturally come to mind. You should be learning them. So for integers a, b, elements of z, and now the modulus n is another integer, but we should say something about it. We don't normally speak of negative moduli. Yeah, I should do it automatically, shouldn't I? There we go. So, okay, we're not running anymore. So, we certainly don't normally speak of negative moduli, and I don't think it makes sense to talk about zero modulus either. The definition of congruence is that a modulus has to divide something, and zero doesn't divide anything apart from itself. So for integers a, b, and z, and an integer modulus n, and we'll take n to be greater than or equal to 1. Actually good. Yeah. We say A is congruent to B modulo n. If and only if, this is the normal way we quote definitions, we give the state the concept we're defining, and then follow this with an if and only if, and then give the exact definition. If and only if n divides a minus b. I.e., so in other words, a is congruent to b modulo n. This is equivalent to the fact that n divides the difference a minus b. Okay, so that's the definition of it. For full marks, you have to say something equivalent to that, something nice and precise. The other bit there was, it said, how does it relate to the remainders left when the integers a and b are divided by n? So, alternatively, we can define congruence as saying that a is congruent to b mod n if and only if when a, b are integer divided by n, they leave the same remainder. So if you write a as some quotient q1 times n plus a remainder r1, so where r1 is strictly less than n, q is an integer. Similarly, you can write b as q2n plus r2, where this is another small remainder, strictly less than n, and q2, of course, is again an integer. So a is congruent to b mod n. This is equivalent to saying r1 is equal to r2. Okay. That number r, that's what's termed the standard representative of the congruence class of A or B modulo A, smallest non-negative representative function. Is that okay? The questions or queries about that? So that was a little 4-mark definition question at the start. And part B asks about the Euler-Toschen function. It says, state clearly the definition of the Euler-Toschen function phi and prove that for any prime p and exponent n, phi satisfies, and then we've got that familiar formula then for phi of e to the power n. So a couple of things needed here. First of all, we need to give the definition. Yeah, so Euler-Toschen function phi is defined by, we'll say something about what its domain is in a moment. This is going to be defined for positive integers, maybe integers strictly greater than 1. Yeah, by n greater than or equal to 1. Put that down at the end though. By phi of n is equal to the number of integers n, such that what we're counting here is the number of integers between m and n, and that n must be co-prime to n. Or equivalently, you could give that range because n is never I was going to say you could say less than or equal to n minus 1, but then you have to worry about what happens in the case n equals 1. Still be 1, so no, slightly different. Okay. So that's the definition we gave for the Euler-Toschen function. To count the number of integers less than n that are co-prime to n. This is also the size. I think you would get full marks just for having that, but I would like to include this because it's the reason 5n is important. It's the size of the multiplicative group of integers under multiplication, or just a group of integers under multiplication modulo n. So in notation there, we have 5n was the size of Zn with the superscript of multiplications. It's a group of integers under multiplication modulo n. That only consists of the congruence class. It consists of congruence classes because it's multiplication modulo n. And it's only those congruence classes of integers that are coprime to n. Okay? Because the other ones that are not coprime to n, they don't have multiplicative inverses. So they don't get admitted into the group. Because groups have to have inverses. Okay. So now we want to prove the formula for 5 prime power of prime. Okay. So the claim here is that for p prime and any exponent, basically n greater than or equal to 1, that 5 of p to the power n is p to the power n minus 1 multiplied by p minus 1. So we want to prove this. Okay, so you're in an exam and you're sitting there and you're looking, you think, well, I have to prove this now. Maybe several thoughts come to mind. I mean, it does kind of look like a natural case for a proof by induction, because it seems to be a whole family of statements indexed by the integers n equals 1, n equals 2, n equals 3, and so on. But I think we get this slightly more directly without having to use induction, because the thing about this argument, it was a counting-based argument. So it was, and in some ways, so I hesitate to use words like simple or straightforward, because these things are tough when you're studying them for the first time. But I use the word simple not just to say, oh, it's easy, nobody should know it, but just when you think about the technology involved in the proof of it, it really was a simple argument. Putting all the things in front of us, all the integers in the relevant range between 1 and p to the n, and simply carefully counting the ones that are co-prime to p to the n. So it's simple in that sense, just throwing up all the objects in front of you and counting the relevant ones. Okay, getting the details down is a little bit more tricky, and you have to use the definitions carefully and make sure your argument is watertight. But in that sense, it's a simple counting type argument. So that's the basic, that would be the nub of the argument that I would learn off by heart, so to speak. It's this simple counting argument using the original definition of phi, and then start to reconstruct it. Okay. So by definition, phi of p to the n is the number of integers m in the range 1 less than or equal to m less than or equal to p to the n, satisfying GCD of m and p to the n is 1. Okay? So you can imagine all of these here, 1, 2, 3, 4, etc. Big long list of them all the way up to p to the n minus 1, as far as p to the n. Okay? So these are the candidate n's. so to speak, the n's in the range 1 to p to the n. But we only want to count the number of them that are co-prime to p to the n. So before we leap into that, we just carefully consider this thing. So how is it that something has a greatest common divisor with p to the n of 1? So the focus here is p to the n. What are the possible divisors of p to the n? What possible divisors does p to the n have to possibly share with these numbers n that are less than n? Okay. Well, you see, since p is prime, the only divisors, and this is where we're using the fact that p is prime, the only divisors of p to the n are 1, p squared, etc., all the way up as far as p to the n minus 1 and p to the n itself. And this is certainly because p is prime. Right? If you just have a general number of x to the n might have loads of divisors apart from just the lower powers of x, because x might itself be composite and have 2 different divisors, and so lots of different powers of those divisors and products would be divisors of x to the n. But for a prime integer p to the n, there are no factors to be found inside p except for 1 and p. So the only factors that are to be found of p to the n are just all the smaller powers of p. So basically, if p, then the greatest common divisor of m and p to the n will be at least p. Okay, will be at least p, and since p is a prime number, will hence be strictly real. And if p does not divide m, then the GCD of m with p to the n, m with p to the n will be 1. Okay. If m does not have a factor of p inside it, then it cannot share any common divisor with p to the n except for this first one. Okay. So all the other common divisors, all the other divisors of p to the n, they all have at least a factor of p. So once that is clearly stated, we can then ask, so we can count the m in the range above, meaning this range 1 to p to the n, which are not co-prime. As all the multiples of p. Namely, and this is what I mean by simple, what multiples of p are there? Well, there's p. There's 2 times p. There's 3 times p. There's 4 times p. 5 times p. These are all the multiples of p that there are in increasing order. Just every integer times p, increasing integers. How high can you go? Well, you see, we have to stay within this range of 1 to p to the n. So the highest up we can go is p to the n minus 1 multiplied by 2. That's the very last one, p to the n itself. Yeah. So these are the integers from this range which are not co-prime p to the n. And how many of them are there here? And this is what I mean by simple counting argument. You just count them as 1, 2, 3, 4. So p to the n minus 1. In the ID, p to the n minus 1 such n. Such integers. So the remaining ones, the remaining m, i.e. the m's not on this list here, must all be co-prime. They must all be co-prime to p to the n. So phi of p to the n is the amount remaining there. But there were p to the n integers there to begin with, 1, 2, 3, up to p to the n. So the ones remaining are the ones which are not on this list, and there are p to the n minus 1 there on that list. And that's just a different way of writing down p to the n minus 1 times p minus 1. Just simple factorization I did. As required. So I would suggest that it's not that you learn something like that off by heart, but that you remember the essential ingredients. Essential ingredients is the nature of that argument is it's a kind of simple counting argument. A big bunch of elements, 5 p to the n is elements from that list with a certain special property, namely that they're co-prime to p to the n. And we arrive at how many there are by counting the ones that don't satisfy that property. So then let's see, yeah, so I got to pick out the numbers here which are not co-prime to p to the n. How could something be co-prime to p to the n or not? That's to do with whether or not it's divisible by p. And that is because p is a prime number. So it would be good to stress, you know, definitely somewhere in this argument you have to make use of the fact that p is a prime number. And that's crucial. Because p is a prime number, it means we can recognize that the only divisors of p to the n are these smaller powers. Smaller powers of p. And then so that gives us that it's co-prime to p if you're not divisible by p. If you are divisible by p, you are not co-prime to p to the n. So therefore, you can just simply count multiples of p. Okay, so that would be a kind of argument there. We get you full marks for part B, the definition, and that proof. Any questions about it? So like a harder question would be, maybe a slightly harder question would be like prove the full multiplicative formula for phi of n. So just a little comment, this leads to the full formula for phi of n, and this is if n factorizes as primes like this, canonical form for n, product of prime as a product of powers of primes pi, that implies that the value for phi of n, the product of all these, so you basically taking this pattern here for each prime. So this leads to this full formula by using the multiplicative property of phi. Multiplicative property of phi is, remember that if GCD of A and B is 1, this is in the number theory sense, this is what we mean by a function being multiplicative. If the two factors A and B are co-prime to one another, then the value of the function phi evaluated on AB factorizes as phi A times phi. This property always holds without the co-prime condition, then it would be called completely multiplicative. Just plain multiplicative in the number theory sense means you have to have this co-prime condition. If they multiply the backside of number 30, you probably just need a function acting like this. Okay, so that was 10 marks. That was half that question. So, yeah, reasonable amount to produce for that. Part C. So use the concept of congruences in the Euler-Toshin function to determine the remainder left from 2014 to 1964 divided by 25. 2014 was relevant because of the year it was. I'm not quite sure where the 1964 came from. I might just put that out here. I might have some special meeting. So how do we do this? So what might the relevant properties of congruences in Euler-Toshin function? Well, we can certainly say, so this is quite similar to something that we asked about in the coursework. So firstly, we simplify the base of this tower. So 2014 is congruent to what modulo 25? $14, of course, because 25 is a factor of 100. If you take off the hundreds there, you're left with 14. So yeah, 14 modulo 25. So that implies that 2014 to whatever the 1964, this is going to be congruent to 14 to the 1964 modulo 25. As you clearly given the justification for that simplification, then we would want to call upon Euler's theorem. So by a result of Euler, if the GCD of A and N is 1, then A to the power of phi of n is going to be congruent to 1 modulo. So we can make use of that here. This is the property that allows you to simplify the exponent. This will allow us to simplify or reduce the exponent. So it's certainly true that the GCD of 14, 25 is 1. And phi of 25, well, of course, 25 is 5 squared. And we just, in the previous part, seen how to evaluate phi of power of prime. So this is 5 by 5 minus 1, so that's 20. So then what we want to do is simplify the exponent modulo 20. So 1964 is going to be some multiple of 20 plus a remainder of 4. And the factor, this number here will be 19 times 5, 1900 plus 3 to the 60. So that's 50, 45, 95, 98. All right? 98 by 20 is 4. So our 14 to the power 1964, which is equal to, and using rows, this is 98 by 20 plus 4. Using rules of indices, this is 14 to the 20 to the 98 by 14 to the 4. That's just straight arithmetic, manipulating indices, but when you introduce congruences, modulo 20, modulo 25, this then becomes, using this result of Euler's theorem, 14 to the 20 is going to be congruent to 1. So this is just 1 to the 98 by 14 to the 4. So this is just congruent to 14 to the 4 modulo 25. So this gets, simplifying right down, which we now evaluate by hand, I guess. Not whether there are simplifications defined, I don't think. Well, 14 is 2 by 7, so 14 to the 4 is going to be 2 to the 4, 7 to the 4, 2 to the 4 is 16, 7 to the 4 is 7 squared. 7 squared is 49, modulo 25 is minus 1, isn't it? So when you're scared, you get plus 1, so yeah. 49 is minus 1 modulo 25, isn't it? Because it's 25 plus 24. So 16. Wouldn't worry too much about laboring the justification there. You reduce things a lot. Just a little side calculation here. So the answer seems to be 16 modulo 25. Agreed. But important elements to stress there is to clearly explain how you simplify the base, clearly explain how to simplify the exponent, clearly show all of those being used. I'll give a okay, one little point. The question wasn't phrased in terms of congruences. The question was phrased in terms of what remainder is left behind. So since 2014 to 1964 is congruent to 16 modulo 25, as we've seen, and 16 is small, meaning it's less than 25, sorry, strictly less than 25. Then 16 is the remainder. 16 is the remainder left after 2014 to the 1964 is divided by 25. And this is by the point explained in part A. Yeah, in part A, we explained that two things are congruent if and only if they left the same remainder after division by modulus. Of course, 16 is as small as you can get, modulo 25, so the remainder is going to be 16. Okay, any related questions on that? Any related questions to any of those concepts that you'd like to ask about or check? So. Okay, so moving on to question 3. Let's look at about the statement of question 3. Everybody got the part C in there? So part C from 2014, the first part was again on the theme of prime numbers, or their opposites, composite. And then part B on the process of solution lifting. So part B is kind of a technical kind of formula following exercise. And the required formula is in the required kind of formulae is in the statement of theorem. Which chapter is it in? It's in chapter 7, theorem 7.2. That is included on the handouts. It's quite kind of itty-bitty formulas that describe that process of solution lifting. Part A is another little proof type exercise, and it is one we proved in the course. And this is about gaps between prime numbers. And this is nice because it's kind of a companion result to the twin prime conjecture. Twin prime conjecture says that infinitely often the gap between consecutive primes is as small as possible. Smallest the gap between consecutive primes can be is 2, of course. Then you have a pair of twin primes. Twin prime conjecture says that there's an infinite number of twin prime pairs. We don't have a proof of that at all yet on Earth. You know, so